Hello, I'm Ford Mays, Systems and Applications Engineer at Venable Instruments. In this video, I will show you how to use the synthesis and simulation features of Venable's stability analysis software to create and simulate a feedback circuit for a power supply modulator and combine data sets to observe the overall loop gain of the power supply. In this tutorial, we will use the error amplifier synthesis and circuit analysis feature found in Venable's stability analysis software. The synthesis and circuit analysis window has 5 tabs: loop design, component values, circuit model, circuit analysis, and frequency analysis. Here we see the Bode plot of the modulator that we wish to create a feedback circuit for. This modulator, also known as a power stage, a switch, or plant, was measured with a Venable frequency response analyzer. The first step is to specify our feedback circuit crossover frequency and phase margin. We will do this by selecting the modulator plot by left-clicking on it and creating a slide bar cursor by clicking on the slide bar button. We shall set the desired crossover frequency by either clicking and dragging the cursor or typing in the frequency. The 0 dB crossover frequency is typically set between 10 to 20% of the converter switching frequency. Next, we will import from the modulator measurements of crossover frequency, gain at crossover frequency, and phase at crossover frequency by clicking on Import to Analog Synthesis window at the top of the screen. The Error Amplifier Synthesis and Circuit Analysis menu will then open with these values populated. Next, we set the desired phase margin, where 60 is the default value, to finish entering the measured data of the feedback circuit under Overall Loop Circuit and Control to Output or Modulator Circuit. We need to characterize the error amplifier circuit. First, we select the maximum circuit complexity or amplifier type. The Type 2 amplifier is used for current mode control, and the Type 3 is used for voltage mode control. The amplifier circuit is inverting, is a default, and is checked because most modulators are non-inverting, and the overall feedback has to be negative. The correct amplifier topology is determined from the converter IC datasheet. Typically, transconductance amplifiers are used in current mode ICs with Type 2 amplifiers and regular or voltage amplifiers in voltage mode ICs with Type 3 amplifiers. The input resistor is a user-selected value for the top resistor in the voltage divider between the power supply output and the error amp inverting input. The input voltage to the amplifier is the converter output voltage. The error amplifier is almost always part of the converter chip, as is the voltage reference. We get the reference voltage value from the datasheet or app notes, which is also the common mode voltage, since the reference is tied directly to the non-inverting input of the error amp. Op-amp selection or error amplifier values such as the bandwidth, gain, and transconductance are also pulled from the converter datasheet. The internal R value is used to set the corner of the open loop gain for the regular or voltage amplifier. 1 kiloohm is the default value. The internal R value of the transconductance amplifier corresponds to the output impedance of the amplifier and is calculated by the Venable software. Error amplifier values can be saved or recalled from an op-amp file. This information in this tab can also be saved and recalled for future use by selecting Save Design File. Next, click on the Compute Component Values button. This will automatically take us to the Component Values tab. Here we have the synthesized feedback circuit schematic and component values. The component tolerance and value rounding can be selected here. The schematic can be printed from this tab as well. The user can change the values of the components and see the effect in simulation. Clicking the Make Circuit Model from the Component Values button takes us to the next tab, Circuit Model, where we have the Venable Spice-like model. We can open a saved circuit file for editing or save the current file for future use. Next, click on the Go to Circuit Analysis tab button. In this tab, we set up the parameters for AC simulation. We set our sweep frequencies, which should be the same that was used for sweeping the power stage or modulator. Use the default input and output nodes 1 and 2 respectively of the circuit model and check and make sure that the sweep parameters are the same as used for the power stage. Next, click on the Compute AC Analysis from Circuit Model button to begin the AC simulation. You will see the next tab, Frequency Analysis tab, with the numerical results of the simulation. You can open a saved AC file or save it in this tab. When you click on the Plot button, you will see the graphical results of the simulation as a Bode plot. From here, we can now mathematically combine the measured modulator data with the simulated feedback circuit data. To combine the data sets, we use the navigation window to select the data set for the left operand, in this case the measured modulator data, and the simulated feedback data for the right operand. Since we want to see the overall loop gain of the system, we select Multiply. Now click on the plot to see the results. Now we can see the results of our efforts. Using the slide bar feature, we go to the unity crossing point of our loop gain plot and verify the desired crossover frequency and phase margin. Thanks for watching this tutorial about synthesis and simulation features of the Venable Stability Analysis software. This powerful tool simplifies loop compensation and shortens the design cycle by providing an easy-to-use application that is based on Dean Venable's K-factor analysis. More information about stability analysis, frequency response analyzers, and software, as well as application notes, can be found at our website www.venableinstruments.com.